right side by side. One is Jupiter and the other is Saturn. So I'm going to share my screen here and show you an image of Jupiter taken with this telescope, with our 36-inch reflecting telescope. Um, this is just a single short exposure image. It's not processed or anything like that, but it gives you a pretty good idea of what you would see through our telescope if you were to come up here to Chabot and look through one of our telescopes. In the pre-COVID days and in the post-COVID days, we opened the telescopes for public viewing. Right now, we're in the middle of the COVID shutdown, so we can't do that, but we will be opening up sometime next year, and you'll get to come back up to Chabot and look through our telescopes. And this is an idea of what you would see if you saw Jupiter. Jupiter is the largest planet in our solar system. It's the fifth planet from the sun. So Mercury, Venus, Earth, Mars, and then Jupiter. Jupiter is 88,000 miles in diameter. It's 11.2 times the size of the Earth. And Jupiter rotates very rapidly. A day on Jupiter is only about 9 hours and 50 minutes long. Jupiter is a gas giant, so it doesn't really have a solid surface like the Earth does. What you see is the tops of a very thick layer of clouds that actually goes thousands of miles deep. Because Jupiter rotates so rapidly, high and low pressure areas in the clouds actually wrap around the planet. So you see what looks like stripes on the planet, like a beach ball, but those are actually high and low pressure areas. The dark ones we call belts, and they are typically the result of low pressure areas in the atmosphere, and the light ones are called zones, and those are high pressure areas. But you get a hint when you look at this, you get a little bit of a hint of the turbulence between between the belts and the zones. There's a lot of turbulence there, which produces a lot of eddies and swirls and little mini cyclones and so forth. This image doesn't show it, but there is also one very big cyclone on Jupiter, and that's the Great Red Spot, which would be in the southern belt. This is the southern belt here. Jupiter's gravity is very strong. It has the strongest gravity of any planet in our solar system. In fact, if we were to take away the sun and take away the Earth and just suspend you out in space, you would fall onto Jupiter. That's how strong its gravity is. And because of that, Jupiter has a lot of moons. I think the count is somewhere north of 80 now moons orbiting around Jupiter. There are 4 moons that are especially interesting, though. Those are what we call the Galilean moons. They were discovered by Galileo in the year 1610 using a very primitive telescope. And he discovered them because they're the biggest moons of Jupiter. There's 4 of them: Io, Europa, Ganymede, and Callisto. And they're pretty good sized moons. 3 of them are actually bigger than our own moon. But they orbit very rapidly around Jupiter. In fact, Io, which is the closest to Jupiter of the 4 moons, it takes just under 2 days to make one complete orbit around Jupiter. Now, we can't see it in this image here, but when you look at Jupiter with our telescope, you can actually see those 4 moons. And if you look at Jupiter at one point and you see where the moons are, and then you come back even just a half an hour later, you will have noticed that Io has changed position. So that's how rapidly it orbits around the planet. It's pretty interesting to watch.
Question for you, Gerald.
Okay.
Is that the red spot in the southern band all the way to the right?
Right there?
Yep.
Yeah, I think that might be it. Yes.
Okay.
Yeah. Now, because Jupiter rotates so rapidly, the red spot is only viewable for about a 4 hour period on each rotation. So it's kind of hit and miss, and whether you get to see it at whatever time you happen to be observing Jupiter. Um, and if you miss it, you got to wait 4 hours till it comes around again. Um, but it is pretty cool when you get to see the Great Red Spot. The Great Red Spot has been shrinking a little bit lately. It's been there for at least 100 years and probably a lot longer than that. But we have noticed it's kind of shrunk a little bit in the last few years. It's
It's
also
been changing color.
changing color, right?
Yeah.
Yeah. One of the interesting things is that it actually drifts. So it changes position relative to what we think of as a fixed coordinate system on Jupiter, which is hard to do with a gas giant, but there actually is a way to do that based on its magnetic field. Um, and it turns out that the Great Red Spot drifts about 15 degrees per year relative to that fixed coordinate system. So we're not sure what exactly is causing the Great Red Spot and why is it that it slowly drifts like it does. So
Let me
anyway,
interject just for a second, Gerald.
okay.
We have a concerned viewer asking if Chabot is in the fire danger zone. Well, pretty much all of the Bay Area is in the fire danger zone right now. Hopefully, we're not really too much affected by it because we are down close to the bay. But thanks for asking. That's a very nice.
Very nice
thought.
of you. There are no active fires right now in the hills on the East Bay that I know of. So
no, but they're really worried about it.
However, tomorrow there is a red flag warning that starts for this area at 11 o'clock tomorrow morning.
Right.
So yeah. We will be in the zone tomorrow.
Yeah. Everybody be careful tomorrow.
Yeah. When the winds kick. And by the way, the parks all around us. Chabot is in the middle of a group of parks. We have Redwood Regional Park on one side of us and Joaquin Miller Park on the other side of us. And those parks are all going to be closed tomorrow because of the red flag warning. So this is Jupiter. It would have been the first thing we looked at. I'm going to unshare that and switch to the next thing we would have looked at. If I can find it. Bear with me here for a second.
It's up there.
Oh, yeah, it's in the sky, right? Oh,
well, not in our sky. It's too foggy.
It's only in Gerald's sky right now.
Right. Okay, here we go. So the next object we would have looked at is something most people will recognize right away, the planet Saturn. And this is another one of those unprocessed images taken with this telescope. We can see the rings. We can even see a little bit of belts and zones on Saturn as well. And a lot of people see this image, and when they look through our telescope and they see Saturn, they're surprised to see that it's so pale. It doesn't have much color. If you look on the internet or look in some astronomy books or magazines, you'll often see pictures of Saturn where there seems to be a lot more color. And that's mostly because of how those images were processed. One thing you can do when you're processing images is assign colors, more contrasty colors to what are really very subtle differences in shading. And by doing that, you bring out a lot more detail in the image, but you end up with a false color image. This is a true color image. Saturn is actually pretty pale in appearance, has a little bit of a tan coloring to it, but not a whole lot of other colors to it. And you see the rings, you see a gap in the rings right here. We call it the Cassini Gap or the Cassini division. If you got up close to the rings, you would see that that's not actually a gap. It's just an area where there's a lot fewer particles in the ring. The rings are made up of ice particles, chunks of ice. Most of them are about the size of your fist or so, but there are quite a few that are a little bit bigger, the size maybe of a desk. And the ring plane is actually very thin. It's only about 10 or 20 meters thick in most areas. There are a few places where it's been disrupted by little mini moons that are embedded in the rings. But it's a pretty thin ring plane. the rings change their angle throughout the Saturn's entire year, which is about 30 years long. So we often see the rings at different angles, and sometimes we even see them edge on. And when we see them edge on, they almost disappear. Um, but right now, if we were viewing tonight, this is about the angle that the rings would be at. Um, Saturn also has quite a few moons. I think it also has more than 80 moons. Um, most of them are quite small and can't be seen with our telescope at all. It does have one really big moon, the moon Titan, which is one of the few moons in the solar system that has an atmosphere. In fact, it has a very thick atmosphere consisting of a lot of methane and nitrogen. And one of the interesting things about Titan is that methane, because it's so cold on Titan, that methane actually turns to a liquid and it rains on Titan. And there are lakes and streams on Titan that are not water. They're liquid methane and liquid ethane. So very different place to be. But when you look at the features, it looks a lot like what you see on Earth, where rivers and streams flow and erode the surface. But they're rivers and streams of liquid methane rather than water.
And what people might want to remember is that when we sent the Cassini spacecraft to Saturn, it had a exploratory robot that was sent to Titan.
Right.
And
Huygens
called the
probe.
Huygens, right?
Right.
Was that the Huygens?
Huygens probe. Yes. Yeah.
So
Yeah.
we know a lot about the atmosphere because we were able to actually sample it.
One quick question here from our audience. Can we use the telescopes during a PSPS? Well, for those not in the Bay Area, a PSPS is a power safety, a public safety power shutdown.
I was wondering what that was.
Yeah.
I had no idea.
Pretty much no. This telescope is computer controlled and we need the computer on. Our other two telescopes are not computer controlled, but they do use electric motors to run the drives to make up for the rotation.
Opening the dome.
And opening and closing the domes
Right.
is really difficult without power.
We have to use a crank.
So yeah, we don't do things pretty much when we don't have power here.
Yeah, in fact, we are forecast to have a PSPS tomorrow evening, starting somewhere between 8 and 10 o'clock here. So we have to shut down all our systems tonight after we're done here so that we don't get any shocks when the power goes off or when it comes back on. So that's just, what we do to protect our equipment.
Yeah. There's another interesting question here. Why does Titan have an atmosphere, but the larger Ganymede doesn't? Well, that's a tricky question.
It's a great question.
It's a very good question.
Yeah.
And I wish I had an answer for you.
Well, it could be because of the plasma field around Jupiter would strip away atmosphere from close bodies. I'm thinking that might be part of the reason.
Yeah.
That's a great question.
I'm not sure that size has everything to do with,
me
with
neither.
an atmosphere.
Triton, which is one of the moons of Neptune, also has an atmosphere. So not sure what the reason is. So you stumped the stars. Congratulations. So I got one more planet to share with you, if you'll bear with me for here just a minute. Went the wrong direction. Hang on here. There it is. All right. So the third bright planet that's up is in the eastern sky. And if you look out, if you happen to have clear skies and you look outside, you'll see a bright kind of orange colored bright star, which is actually the planet Mars. And this is a unprocessed image of Mars taken with the telescope right behind us. Mars is small. It is only half the diameter of the Earth. So it's much smaller. It's also darker in appearance because it has dark mountains and cratered surfaces and so on. But it does have an ice cap. And in this image, you can see one of the ice caps up here. It does have polar ice caps. Um, when we look with our telescope at Mars, we don't see a lot of detail uh, because mostly what you're just seeing is differences in shading, much like what you see here. This image is probably one of the better images that we've been able to capture in a single exposure with this telescope. Uh, Again, Mars is about half the diameter of the Earth. It has an atmosphere, but it's a very thin atmosphere. If you were standing on Mars without a spacesuit, it would pretty much feel like you were in a vacuum. The density of the Martian atmosphere at the surface is 1/100th the density of the Earth's atmosphere.
That's
So,
right. We all remember what Arnold Schwarzenegger looked like when he stepped out onto the surface of Mars.
I'll be back.
No.
So we have several spacecraft on the way to Mars right now. What's the name of the Perseverance is the name of the rover that's on the way to Mars, and then there's also a, um, a Chinese spacecraft on the way, and then I think there's one from the United Arab Emirates or something like that.
Yes.
Yeah.
It's the UAE that sent it.
Right. So the Perseverance is a rover similar to the Curiosity rover, which is already on Mars. Perseverance will land in a different location. It has some different instruments on it, but if at first glance it looks a lot like the Curiosity rover. Um, the other two probes are orbiters that will orbit around the planet, and they're all expected to arrive sometime in February of next year. So I know that when the Curiosity, or the Perseverance lands in February, that's on February the 18th. I think we're going to try to do some sort of a live event here on Chabot's Facebook page to follow the landing. All right. So those are the three easy to see planets. There are a couple others, actually, well, yeah, two other planets that are visible with a telescope, but not very interesting to look at. One is Uranus, and the other is Neptune. Both of those are also in the sky right now, but they're so far away that they just look like barely noticeable as a disk when we look at it through our telescope. They almost look like stars, except that they've got a little bit of color to it. And there's a little bit of a disk rather than just a point of light, like with a star.
Hey, I remember a couple months ago we looked at Pluto.
Yeah. Pluto.
Yeah.
In fact, right now in the sky, Pluto's position is actually between Jupiter and Saturn. So they're all kind of clustered together in the same part of the sky. Of course, they are very far away from each other. Just to give you an idea, even though Jupiter and Saturn look close together to us in the sky because they're along the same line of sight, they're actually about 500 million miles apart. So there's quite a bit of separation. And one of the interesting things about Jupiter and Saturn is they are slowly coming closer together from our point of view. Jupiter, because it's closer to the sun than Saturn, it orbits the sun faster than Saturn. Jupiter takes 12 years to orbit the sun. Saturn takes 30 years to orbit the sun. So Jupiter is sort of catching up with Saturn right now. And the two of them will be so close together on December 21st, I believe it is, that they will be viewable in the same field of view of the telescope. Unfortunately, that's going to happen very early in the evening, not too long after sunset. So I'm not sure we're going to be able to show it to you during our regular virtual telescope program, but we're certainly going to try to get pictures of it and make sure you get a chance to see both planets in the same field of view.
A couple more questions.
right.
Again, back to electricity and power shutdowns. Let's see here. It's John wanted to know how did we run the telescopes before electrification? Well, two of our telescopes are very old. Leia and Rachel are both over 100 years old, and they still ran without power. The domes had to be manually moved around, but the telescopes could track and make up for the rotation of the Earth with clock drives that were run just like an old grandfather clock. They had weights and little gears and stuff that would actually drive the telescope just from gravity. So that's how they worked.
That was green technology back then.
Yeah.
Right, very green.
No electricity. So,
Yeah, there was one other really good question about the atmospheres again. I'm assuming it goes back to the moons of Jupiter and Saturn. How were the atmospheres formed? I don't have a clue.
Well,
most likely they formed when the moon itself formed.
Right.
So
Yeah.
it's likely that some of it was a result of comet impacts bringing volatile materials. It's also possible that it was outgassing from the interior of the planet of the moon. If the moon was big enough, it could potentially have had a molten interior at one time. So there's a couple of different sources.
And also capture from the gas cloud that formed the sun in the first place.
Right.
I mean, if you think of our solar system like an over easy egg, right, with the sun in the middle, there's all this material around it, and the planets coalesce and they pick up nitrogen and possibly some oxygen and carbon and whatnot. But of course, we have an oxygen atmosphere on Earth because life created the oxygen atmosphere. Yeah. So it probably started off with a lot nastier substances like methane and just nitrogen and whatever else was in that part of these orbit around the sun.
I'd also like to say that there have to be certain conditions to keep an atmosphere. You might have an atmosphere for a while, and it can get lost very easily. They're a very delicate thing.
Which is what we think happened at Mars.
Right. Yeah, we actually think Mars lost its atmosphere when its magnetic field died. So early on, Mars had a magnetic field. But eventually that because the molten interior cooled, its magnetic field died. It didn't die completely, but it's now extremely weak. And the magnetic field around planets actually protects the planet from the solar wind. Mm-hmm. And so we think what happened was once it lost its magnetic field, the solar wind actually blew the atmosphere right off of Mars. So, we got to keep our magnetic field here on Earth.
Right. Very important for us.
So guys, in addition to looking at the planets tonight, we would have looked at a couple of other objects, what we call deep sky objects, things that are outside of our own solar system. And I've got a few to share with you here. Let's see. One I wanted to show you is called the Dumbbell Nebula. Dumbbell Nebula is what we call a planetary nebula. It's gas expelled by a dying star.
That's a nice one.
This is a photo of the Dumbbell Nebula. This was not taken with our 36-inch telescope, the one that's behind us here. This was taken with one of our other telescopes here at Chabot, our smallest telescope, our 8-inch refracting telescope, the one we call Leia. That telescope was built in 1883 and it still works. So we still use it regularly, and this is an image taken with that telescope. So the Dumbbell Nebula is called a planetary nebula. There are a lot of planetary nebulae out there. This is typical of how most stars end their lives. So this was once a star like our sun. As it grew old, it swelled up it became a red giant star. So at one point it was maybe 1 million miles in diameter during its what we call main sequence. But when it became a red giant, it was more than 100 times that diameter. And a red giant, it's so big that its gravitational hold on its outer layers of gas is very weak. At the same time, you've got a lot of convection going on inside the star that's producing some strong winds that, because of the weak gravity, can actually blow the gas out, the outer layers of gas, right off of the star out into space.
Pardon me, Gerald. We got a request for you to up the volume on your mic,
Not
or
sure.
maybe
I'm
closer.
not sure I can do that. Is this any better?
Yeah, it's a little bit better.
Okay, so the red giant is blowing gas out into space for about 100,000 years. And then eventually what happens is it's exposing the inner layers of the star where it's hotter. And at the same time, it's running out of fuel at its core, which is where the fusion process is going on, which creates the outward pressure on the star. And when that fusion process stops, whatever's left of the star collapses and becomes a very small object called a white dwarf. White dwarf emits ultraviolet radiation, which goes out and it hits all that gas that was being blown off when it was a red giant. And it ionizes the gas and causes it to glow. So what you see is this glowing shell or bubble of gas surrounding the white dwarf. The white dwarf is right at the center. And this is this bubble of gas that was blown off by the red giant before it became a white dwarf. And this is typical of how most stars die. This is how our sun will die. And what's interesting about planetary nebulas is that they have all kinds of different shapes. They're often symmetrical shapes. Sometimes they look like hourglasses. Sometimes they look like butterflies. They can have a lot of different shapes. And so they're very interesting to photograph because of, they look so different. So many of them look so different. But it's all basically the result of the same process. All right. And let's see, I think this one is about 1,250 light years away. It's hard to measure the distance to planetary nebulas, but we think it's around 1,200, 1,250 light years away. All right.
Nice.
Okay. I got one other really interesting object to look at. We talked about the planetary nebula, and that's how most stars die. And people think that most stars die in a supernova explosion, but that's not true. Most stars die as that slow process of becoming a planetary nebula. It's only about 10% of the stars that die in a supernova explosion. And those stars are the stars that are really massive, like more than 8 times the mass of our sun. And when those stars reach the end of their lives, they explode. And so I've got an image here that shows the remnant of a supernova explosion. And here you see it. This is called the Veil Nebula. It's actually part of a much larger cloud of gas shed by the explosion of a supernova in the constellation Cygnus Swan. So you see all this color. The red color is primarily the result of hydrogen. And then you see also some blue color that's probably from oxygen or nitrogen. But it's mostly reddish in color. And we call it the Veil Nebula because it looks like a veil or a filament type shape out in space.
It's a really spectacular object to look at through an amateur telescope, but if you want to do that, you have to find a very dark site. You can't see this from the city, at least through a small telescope. And you can also purchase special filters for your eyepiece that bring the spectrum of the Veil Nebula and other similar nebula out so you can see them more easily. And this is a great photograph.
Yeah, and this was taken with our 36-inch telescope here at Chabot.
Nice.
All right. Okay.
Speaking of which, I got something I wanted to share here.
Yeah, go ahead.
Let me see if I can. Tell me if you see this photo come up.
Let's see. Yes.
Yes.
Okay, great. So over the last several weeks, we've been looking at double stars and talking about different stars as we slew to and from them while we're sinking the telescope to the night sky. And we've made some comments about the colors of the stars. We've looked at doubles where one of them is blue and the other one is red, and then we looked at a white and red pair last week. I found this today, and it is a chart of all of the different star colors and their associated temperatures. So you can see that Betelgeuse, which someone asked about earlier, Betelgeuse is 3,000 degrees centigrade. And if we look at another star in the Orion constellation, Rigel, it's at 10,000 degrees centigrade, actually 11,000 degrees. So the chart is showing that the blue stars are much brighter, much hotter than the red stars. And our star is somewhere right in the middle. It's in the Goldilocks zone, I guess. And you can see our sun is 5,000 degrees centigrade, roughly 5,000 degrees centigrade. And one of our nearest neighbors, which science fiction writers always love writing stories about because it's close enough to conceive of going there, Alpha Centauri is also in the 5,000 to 5,500 degrees centigrade range. And how do we know? How do we know how hot stars are, to create a chart like this? Well, basically, we can look at the spectral lines of a star, and we can look at that spectrum and know the relationship between spectra and temperature. And there are 2 or 3 types of approaches to finding out the temperature of a distant object. Looking at the spectra is one of them. There's also a way where you can look at light through 2 different types of filters, and the ratio of blue light to red light will tell you what the temperature of the star is, and there's various other methods as well. But I thought this was a nice chart to demonstrate the concept.
Now notice that in this picture, the sun is shown as white, and most people find that surprising. But if you were outside of our atmosphere, the sun would appear white. The reason we see it as yellow is because sunlight is filtered by our atmosphere, which scatters the blue part of the spectrum, which is why we have a blue sky. And it's also why it makes the sun appear to be yellowish.
Cool. Yeah, I just turned down the volume in my headphones. Now I have an easier time talking. I was getting this really weird echo. So I was having a hard time forming words. I kept hearing myself. Okay, anyway, I wanted to show you this.
That's hard to do. There's a question, if we see our solar system, all terrestrial planets are close to the sun and all gaseous planets are farther away. But solid Kuiper belt objects are farther away yet. Can we comment on that? That's just kind of random. Not all solar or all star systems are like that. Sometimes there are gaseous planets in close, and sometimes they're not. I'm not sure.
I think that's right. And I remember going to a talk several years ago where the theory was that the various planets that we see today in our solar system may have looked very, very different early on in our solar system, and we may have had additional gas giants that actually were closer into the sun and eventually were absorbed by the sun. And that may be a future for Jupiter and Saturn if given enough time. But it was kind of this material science approach to the entire solar system, and looking at how the gas giants were formed and that they may actually spiral inward towards the sun over time. So different solar systems in the galaxy, or in any galaxy, maybe in a different configuration depending on where they are in their life cycle.
Yeah, there's no necessarily set pattern for that.
Yeah, we've discovered several thousand now exoplanets, planets orbiting around other stars. And it's actually very common for us to see giant planets orbiting very close to their star. In fact, quite often even closer than Mercury is to our sun.
Mm-hmm.
All right. So what else we have to share? Oh, I have something.
You have something.
Yeah.
It's your turn for
we
Osiris.
We had a interesting event here recently. The spacecraft known as OSIRIS-REx has spent the last year or so orbiting around an asteroid called Bennu. Bennu is what we call a near-Earth asteroid. I've got a little animation of Bennu here. So I hope you can see it there. And Bennu is a near-Earth asteroid. It's in a very convenient orbit that allows fairly easy access by spacecraft from Earth. And so OSIRIS-REx was sent there. It's been in orbit around the asteroid for about a year. And its ultimate mission was to collect samples from the surface. So for quite a while now, they've been, mapping the surface, trying to figure out what's the best place to take a sample from, because it's kind of like it's a one-shot deal. You do it and hope it works, and if it doesn't, you're out of luck. So, that's been in the works for a while here, and I wanted to show you. Just a couple of days ago, they actually did the sampling. And so I have a very simple animation here showing the sample probe touching down on the surface of Bennu and collecting a sample. It's got like a little inflatable bag. It's not actually inflatable. It's like a scooping bag that grabs a sample, and it will collect it and then bring it back into the spacecraft. And then they have to weigh the sample, and they have a very interesting way to do that. They spin the spacecraft, and the amount of spin for a given amount of energy depends on the mass of the spacecraft. So by spinning it before and after they collect a sample, the difference is a function of the increase in mass that they collect off the surface of Bennu. And so that's how they're going to weigh the sample. Now, one of the things I want you to notice is how rocky and how gravelly the surface is. Bennu is what we call a rubble pile asteroid. It's not a solid rock. It's not a solid chunk of iron. It's a big pile of smaller rocks that have clumped together because of gravity and because of electrostatic forces. In fact, even as it spins around, if other very small micrometeoroids and things like that hit the surface, they can actually knock some of those smaller rocks off the surface. And when OSIRIS-REx first arrived at Bennu, they were surprised to see every once in a while a little pebble or rock come flying off the surface, and they couldn't figure out what was going on. And eventually they figured out it was because small micrometeoroids and things were hitting the surface and knocking rocks off the surface. And because the gravity is so weak, they just went flying out into space. All right.
Cool. So
All
we
right.
have a
So
question.
I'm
go ahead.
sorry, just to
Go ahead.
follow up on what you just talked about. How are they getting the sample back to Earth?
The spacecraft is actually going to return to the vicinity of Earth, and then the sample is put into a package in a small probe, which will then drop back to the Earth through the atmosphere. I believe it's going to be dropped into somewhere in Utah, and it'll be retrieved on the ground.
Wow, it's like sending it FedEx.
Yeah. This will be a while though. It'll be 2023, I think, before
it's
Yeah.
gonna take a
comes
while.
That's
back.
amazing.
Yeah.
That's quite amazing.
Yeah.
Now I have some bragging rights to come to.
Good.
Okay. Before I was a full-time volunteer here at Chabot, I worked in the space industry, and I actually designed some material that you see in this image. You see all this black stuff here? This is a special type of insulation that's insulating the instruments inside of the probe there, and I designed that material, and we designed it actually prior to the OSIRIS-REx spacecraft was built. But when the manufacturer Lockheed Martin looked at the material that I had designed, they really liked how it performed, and so they used it on the OSIRIS-REx spacecraft. So every time I see one of these pictures of the probes, I kind of, that's me.
Yeah, well, you should. Yeah,
Very
that's
good.
great.
Let's give a cheer for Gerald.
Right.
Is it a hard material or is it
No,
an insulating soft material?
It's actually a flexible type of plastic,
Got it.
like a thick plastic film, but it has some unique properties. It's loaded with carbon. It's called Kapton, but the Kapton has been loaded with carbon, and then on one side of it, it is aluminized. The side that you can't see is aluminized, and then it has a Nomex reinforcing over it, and it's a very unique type of reinforcing that you don't encounter very often.
And the aluminization is to prevent heat
It actually prevents heat from being transferred into the
into the
instrument.
spacecraft. Yeah.
Yeah, the idea is to keep the instruments within the spacecraft at roughly at room temperature, even
Wow.
though it's in direct, unfiltered sunlight.
Wow.
So without that, the instruments would heat up to well over 250 degrees. But with this insulation on it, which works really great in space, but not very well in the atmosphere. But
That's neat stuff.
Yeah.
Can you get enough of it to wrap my entire house?
Like
It would be.
It doesn't work very well. It needs to be in a vacuum in order to work. Right?
It would only cost you a couple $2 billion, Richard.
yeah,
Don't worry about
Yeah.
it.
It's that's the idea.
I've been accused of living in a vacuum, so
Just to give you an idea, they currently sell this for about $280 a foot.
yeah, okay. Not this year.
It's actually on a weight basis, it's more expensive than gold.
Wow.
That's right.
So we have a question that goes back to your chart, Richard. Why is Sirius so bright? Well, there's a few different reasons on that.
Go for it.
Sirius, first off, is pretty close. It's one of the closer stars to the solar system. It's also a very large star, and it's a very hot star. So it kind of hits all of the things that make stars bright: size, temperature, and proximity to the Earth.
Yeah.
I think that the reason we see it as such a bright star in the sky more than anything else, though, is its proximity, because it's in the 9,000 degree range, and that's only a third of the way up the scale. And the if we look at Beta Centauri or A Crux, they're in the 24,000
Yeah.
degree, but we don't have any of those nearby.
We often think that closeness is the major factor in brightness, but size is also a big thing too. And I think Sirius is pretty big.
So here's an interesting thing that is derived from this chart too. When you talk about closeness being a factor, if you know that Sirius, for instance, is of that particular spectra, right? And you know that all stars of that type are going to be a certain relative brightness, then if you see a star with that same spectrum, but it seems dimmer, you know it's farther away. And you could start to measure how much farther away it is. So it's a whole house of cards that's built upon understanding the intrinsic brightness of a star given a particular spectrum, and then determining roughly how far away other stars are in the galaxy. And that works for understanding the distance from Earth to other stars in the Milky Way. Doesn't work very well for going any farther than that. Then we have to start looking at redshift or supernova or other methods of determining distance. But understanding temperature is a big step to understanding distance as well.
Yeah, it is. But one of the things that we mention often here is the three stars in the summer triangle, Deneb, Altair, and Vega, all appear more or less the same brightness.
Yeah.
But Deneb is much farther away than either of the other two stars.
Yeah.
And
of the 20 brightest stars in our night sky, Deneb is the most distant of the 20.
Yeah.
I didn't realize that.
Yep.
That's really interesting. Yeah.
It's
so bright.
Going back to asteroids, there's a couple of questions that came in that I wanted to address.
Yeah.
Actually, one is a comment from Sabina, who's obviously been following the OSIRIS-REx mission even closer than I have. She says that when they touched down, they actually got too much material.
I heard that. Yeah.
Yeah, I heard that too.
Wasn't that capsule that scoops it up? Was not able to close properly. So
it was leaking. It was leaking material afterwards.
Which is kind of funny because they weren't sure how much they were going to get, and they were afraid they were not going to get enough, so they ended up getting too much.
So what do they have to do? Shake it a little bit and knock some of the excess off, or what?
Stay tuned. I'll research that and answer next week.
Yeah.
Okay. Maybe Sabina can. It sounds like she is following this pretty well. There was another question also, and that was: are all asteroids similar in composition? The answer is no, they are not. There's quite a variety of asteroid compositions. Many of them are rubble piles like Bennu. In fact, there is a Japanese spacecraft that is just recently visited another asteroid called Ryugu, which looks very similar to Bennu. It's a different size asteroid, but in terms of its shape and composition, it looked very similar to Bennu. But you have a lot of rubble pile asteroids. You have a lot of asteroids that are what we call monolithic. They look like a solid rock, and they can have different compositions. They can be composed of silicate rocks, much like what you find on the surface of Earth. They can be composed of metals and different amounts of metals, and some of them can be almost all metals. A lot of them are blends of silicate rock and iron and nickel, and some of them are solid iron and nickel blends. So there's different compositions.
It looks like Sabina did come back with a good answer here on how they're dealing with this. So the method of trying to preserve the sample is to get that bag closed faster than they initially planned. So instead of very gently closing it, they're going to
Slam it.
Slam it. No, so they estimate they'll lose maybe another 10 grams of material into space before it's secured. But Stephen had mentioned that there might be some pebbles that are lodged in the rim where it's supposed to close. So I don't know. It sounds like a tricky problem. Hopefully they'll be able to close it and not lose too much.
Well, they'll figure something out.
Yeah. Right.
Better to bring back too much than not enough.
Yeah.
I just hope they don't come back with the Andromeda strain.
Yeah, that's what I was thinking about when I read about it the other day.
All right.
Yeah.
Well, Richard, you had an amateur photograph.
Oh yeah. Let me get before I show people this. I want to make sure I mention his name and say it properly. All right. So every once in a while, I come across just an amazing effort by an astrophotographer. If I could find my browser here, bear with me. Got to get to the right page.
In the meantime, we have somebody interested in making some money off of asteroids. Is there ever gold on an asteroid?
I was just wondering the same thing.
There might be.
I don't know if there's much gold, and there's probably no oil.
Right.
No reason why we shouldn't find gold on asteroids.
Yeah.
All you gotta do is get there.
Get the right one.
You got to get the right asteroid.
Yeah.
Just like finding the right creek. All right. So this is a astrophotograph by a gentleman named Matt Harbison, and he's an amateur astronomer. And he used a telescope very similar to what typical astrophotographer who's an amateur astronomer uses. It's 127 millimeter refractor. But what's amazing about this photograph, and I'll tell you what it is in a sec, is how deep it goes. And what you're looking at here is the constellation Orion. Here is Betelgeuse. Here is Rigel. Here is Orion's belt, just like the movie. Here's Orion's belt. And here is Orion's sword. And the famous Orion Nebula is right here. And I'm going to zoom in now, just to give you an idea.
Before you zoom in, Richard, there's...
Talk about Barnard's Loop there.
Oh. I was just going to mention that notice how much of the entire Orion constellation has nebula all around it. It's an amazing place.
It's a huge amount of hydrogen in Orion, and there's actually through an amateur telescope there are many regions that are worth looking at if you're in a dark enough sky, and I'll show you one or two of them. But I'm going to zoom in here a little bit, and I'm going to zoom in a really well-known part of the nebula, and here's what's called the Horsehead Nebula, and it looks like a horse. And people always, this is one of the holy grail images in astrophotography. It's a hard image to capture because you have to get the filters right. You got to really be in a dark location. You need a lot of hours to make it a nice high contrast image. This is just fantastic. And I could zoom in even farther on this thing just to give you a sense of how much work went into this. For those of you who are getting started in astrophotography or do astrophotography, I mean, looking at these stars and how perfectly round they are, and pinpoints, is remarkable. And I got to tell you, he put 600 hours of exposure time into this thing. So this is a mosaic with 600 hours total exposure time. And of course, these are stacked images, and a single exposure might be 5 minutes or 10 minutes or 15 minutes, probably differs from region to region in the nebula, and all added together, it's 600. Now, if we
This
move
is an
over,
amazing demonstration, especially you mentioned the telescope. That's a very small telescope. That's
yeah,
not
he has.
much
I
for
believe he
making
has
this.
2 of them on a single mount, so he's able to double his acquisition in the same amount of time. So he'll have 2 telescopes running, and
It's really cool, though.
simultaneously.
Really
So
cool.
here's the Orion Nebula, which people are very familiar with, but this is this is just one of the most beautiful images of it that I've ever seen. Here's the trapezium, 4 stars that we always
No,
point out to people
no,
when we're
no. That's not
looking
it.
through telescopes.
That's not it. The
That's not it?
that bright thing right in the middle of that pocket there.
Where?
Go right.
You almost have to go in closer.
Yeah, go in closer.
Kind of right in the center of your screen
The
now.
brightest region right there.
Oh yeah, you're
Yeah.
right. Those are the 2 doubles. Okay, I thought. I was looking over here. I was saying that looks like a trapezium.
Yeah.
Okay, yeah. Here's the familiar doubles that I.
Nope.
No, in the center.
In the center, the brightest part, right in the middle of the screen. It's so
Right
bright.
here?
It's so bright, it's kind of washing out.
I'm having a
where
hard
they
time
are.
believing that's a trapezium, but okay,
It is.
I will trust you on that.
Okay.
So where are the 4? This one,
No.
or this
No,
one?
they're all in that center
They're
area.
just all in the center area.
They're washed
that's why
out.
that's
Oh,
why
I don't
it's so
see them
bright.
at all.
Yeah,
Right.
that's why it's so bright, because
All
those
right.
4 stars put
All
out
right.
so much energy that when you do an exposure like this, it just completely washes out that region. So
Ah, all right. There you go. But anyway, this one wins.
Yeah.
Yep.
It's really cool.
According to his notes, it took 500 hours of processing time.
Wow.
So he spent a lot of time staring at the computer screen afterwards to produce this. So anyway, the website is https Orion 2020 V as in Victor 5B as in boy .spaceforeverybody.com. It's kind of a long name, but hopefully you guys can catch it.
Yeah, leave it
Maybe-
up there for a few seconds and let people
what
copy
I'll
it
do?
down. That's pretty cool.
Let me open up a notepad document
There
here,
you go.
paste it, and make the font big.
Thanks, Debbie.
What'd she say?
She
In
says that-
Gerald we trust.
Yeah, I know. We have
That's
to.
true.
Yeah, he's much more trustworthy than I am. That's
Gerald
the
is our
truth.
expert.
Yeah. Let me go ahead and share the.
someday when nobody's
Let's
There
just
we go.
post or paste it into the comment section.
Yeah,
there.
it's tough for me to do that
Oh, okay.
from on the phone. So
Yeah.
I'll do that in a minute, but everybody can at least look at it right now.
Orion 2020 VB V5B.spaceforeverybody.com.
Yeah. So anyway, he talks a lot about his equipment that he uses, and it obviously has a link to the image itself, and built a decent interface around the whole image. So. All right.
All right. Well, it's almost 10 o'clock here.
Yeah.
So
Time flies.
why don't we see if there are any more questions coming from the audience? So if you got any questions, put them in the comment section. I encourage you to click on that donate button also. We're up here at the Chabot Space and Science Center, and we are closed right now to the public because of the pandemic. So our revenue stream is down quite a bit, and we do still have to take care of the building. We still have staff here who are developing new content and doing a lot of work. So we do need some source of income. So if you have the inclination, please click that donate button and send us a few bucks.
Hey,
Yeah.
Gerald, do you want to sell T-shirts? I'll
Well,
put up the picture.
yeah, put up the picture because
Yeah.
I don't have the
Yeah. It's
material.
too cold tonight to be wearing a T-shirt.
Really.
Yeah.
So while Richard's digging that up, there's well, he's done that fast. so there's a
I have to make up for the trapezium thing.
So there's a company in Oakland called Oaklandish, and they have partnered with Chabot to print these new T-shirts, which are actually old T-shirts. These were printed several years ago, and they were very popular then. And then they stopped printing them, and then we got a lot of people saying, "Where's that Oakland Universe T-shirt that we love so much?" In fact, one of the guys on the Cassini or the Curiosity rover team down at NASA JPL, he was particularly a fan of it, and he complained several times that he couldn't get the shirt anymore. So Oaklandish and Chabot partnered together, and we've brought out the T-shirt once again. It's called the Oakland Universe, and one of the cool things about it is it glows in the dark. It is available in adult sizes from small to, I believe it was 3X. If you're looking for a real nice 100% cotton T-shirt, this is it. So, and the cool thing is 10% of the proceeds go to support Chabot Space and Science Center. So check it out.
I keep forgetting to order mine. I've got to get mine on order tonight. I'll have to try and do that.
All right.
All right. Okay. Well, how about questions here? Anything popping up?
Somebody asked, where's the donate button? It should be right at the top of your comment.
Yeah, it's part of
area.
it's part of the comment area. There is a circle with a heart. Look for that. It's kind of a pinkish, orangish color.
All right. See if there's any other questions that we need to do.
Let's see.
Did any of you get to observe Mount Stromolo before the tragedy in 2003? I'm not sure I know. Do you know of Mount Stromolo?
That's in Australia, I believe.
It's really familiar to me, and I'm trying to remember.
He says he's kind of scared because
the Mount
he's afraid that 2020 might throw a fire at us. There must have been a fire there or something. I don't know.
Yeah, that's in Canberra, Australia. You were right about that. We're always worried about fire where observatories are. I mean, we tend to be in remote areas. Mount Wilson came very close to getting burned out just a month ago.
Our friends at Tri-Valley
had
a big fire just recently. Yeah,
that's right. The Tri-Valley astronomers in Livermore had an observatory that burned down in the last set of fires.
And the fire burned right up to the perimeter at Lick Observatory.
Yeah, that's right. Yeah, so it's always a concern, and we're fortunate to have a very quick response in the Oakland area for fire, especially after the Oakland fire tragedy, a few decades ago. And hopefully we won't have to, witness anything like that. So I don't know, we feel pretty good about it. PG&E is going to cut the power, so it won't be a power line created fire. But
thank you for the concern, though. That was really
appreciate
nice.
All right. Any other questions?
New comments.
Do any of our telescopes have adaptive optics?
No, unfortunately not.
No.
Yeah, there are some types of adaptive optics that we would be able to acquire for these telescopes without doing major redesign. There are adaptive diagonals and adaptive secondaries and other types of equipment that has come out for the amateur astronomy market. But none of our scopes currently have that.
Right. All right.
Well,
what do you think?
That's about it.
All right. Well.
All right.
Thank you, everybody.
Good night, everyone.
Good night.
We'll see you next week.
See you next week at 9 o'clock.
That's right.